Okay, so first things first, so I don't forget. There's a lot of definitions and things in today's lecture, so I saved it as a PDF and I just popped it into the chat. Um, that way you don't have to worry about writing down all of these definitions and theorems and things as we're going along. You can see that, there's quite a bit of writing and typing here, so you'll have that all on this PDF. So um, just so you're not furiously scribbling down while we're discussing it. Okay, so that's in the chat. I want to do that now so I don't forget. The plan for today is to finish a last problem or two in L'Hopital's rule, and then start our sections on graphing, 4.3, 4.5, and 4.6. We're kind of just combining them all into one big module on graphing. Just a reminder, the midterm exam is this week, so it was available through this past Monday, a couple of days ago, and it'll stay available through 11:59 p.m. on Sunday, the 27th, this coming Sunday. The material is chapter 2 and 3.1 through 3.6. The sample exam was posted last week, so that should give you a pretty good idea of where you stand as far as the exam goes. And you can use formula sheet, calculator, scratch paper, pen, pencil, no open book, no open notes other than what's on the formula sheet, and your calculator can only be a calculator. And I did note last time that I'm not sure if the password screen is working correctly. I don't know if anybody has attempted the midterm exam, but ideally the password screen will work correctly and it'll function exactly the same as the Examity practice exam, where you kind of have to have Examity put in the password and let you into the exam. But it is possible some students last week in a different course, they were experiencing that the password screen was not coming up on the actual exam. So please don't open the actual exam until you're actually ready to take it right then. So make sure that the Examity window or the Examity session is all set up and that everything on that end is set up, and then go into WebAssign, take or open the exam. Ideally, it'll prompt you with the password screen and you do the Examity browser extension, enter the password, it enters the password and you verify it and all that. But just in case that screen doesn't come up and it lets you right into the exam, just be a little cautious and don't open the exam until you're ready to take it. I think I solved the problem with that, but I'm not 100% sure that it worked. So just in case it didn't. And the quote of the day today, as we're working our way into kind of midterm exam time, is "Desperation precedes stupidity" by Dave Ramsey, kind of a financial guru guy. And this relates to things like the midterm exam. If you wait until 9 p.m. on Sunday to try to take your exam, the chance of making a blunder, making an error of some sort, and having a significant negative consequence from that is probably a lot higher than if you give yourself some margin. If you plan to take the exam, say tomorrow, tomorrow during the daytime, during the evening, or today during the evening, if anything goes wrong, there's plenty of margin to work out a solution. Uh, you have a full business day or two. There are lots of options, right? So don't willingly, when you can help it, put yourself in a situation of desperation that often leads to bad decision making. Sometimes you can't help it, right? Sometimes chance is not on your side, but when you can, build yourself in some margin. Okay, so jumping into L'Hopital's rule, the very curt version of L'Hopital's rule is, if we have a ratio P of X over Q of X that limits to either something that looks like 0 over 0 or infinity over infinity, one of those two types of indeterminate form, then we can choose instead to evaluate the limit of P prime over Q prime rather than limit of P over Q. Sometimes that's not helpful. Sometimes it is helpful. A couple of different notes. We are not computing the derivative of the ratio using the quotient rule. We are computing the ratio of the derivatives, P prime over Q prime. Note also for the exam that, if we want the derivative of the function P of X over Q of X, we need to use the quotient rule. So context is important here, right? Most of the time, if we have a function that's a quotient of two functions and we are talking about derivatives, a lot of the times we're going to be applying the quotient rule, particularly in our midterm exam. Section 3.2, product and quotient rules. But in L'Hopital's, it works a little differently. We take the ratio of the derivatives, not the derivative of the ratio. And the second note is that we can't just take any limit if we see, limit x goes to AP of x over Q of x and decide to differentiate the top, differentiate the bottom, and switch to that limit. We can't just always do that. It's only in these types of indeterminate forms, 0 over 0, infinity over infinity, that this works. And I suppose maybe a third note is there are lots of indeterminate forms, and with a little bit of creativity, sometimes we have an indeterminate form that doesn't initially look like one of these two special cases, but maybe with a little ingenuity, we can kind of coerce it to look like one of these and then use L'Hopital's. Okay, so two last examples in L'Hopital's. The first deals with the area of a circle. We're going to go through a proof of the area of a circle. It's going to be pretty rigorous. We'll leave one piece as an exercise, but overall, I think it's going to be a pretty rigorous proof of the area of a circle, and perhaps, or probably likely, the first actual proof of the area of a circle that you've seen. Okay, so what is our goal? We have a circle. If you can believe that that's a circle, you might have to use your imagination quite a bit, with radius r. And our claim is, of course, that its area is pi r squared, a formula that people have known since, grade school or something like that. But I think there aren't very many people who actually can prove this carefully. There are some arguments about cutting up slices and making things kind of look a bit like a rectangle, but they all, somehow involve a limit. Whether the person is saying it or not, to actually make this work out involves a limit. Okay, so the approach that we're going to take is we are going to look at the area of our circle, and we'll have, well, let me switch colors here. We'll have an inscribed polygon, inscribed regular polygon. So here I have a hexagon. This is the inscribed hexagon in the circle is the biggest hexagon that I can put in the circle that fits in the circle. So we'll call this a lower bound for the area, because I see if it's inscribed, if it fits fully in the circle, its area has to be smaller than the area of the circle. And we'll give it a subscript that's the number of sides. So for instance, for the hexagon that's inscribed in the circle, we'll call it L6. It's the lower bound for the area, using a regular polygon of 6 sides that's inscribed. And I need black again. And then we can find an upper bound for the area of the circle using a circumscribed regular polygon. So this is the smallest regular polygon, for instance, a hexagon. It's the smallest hexagon that completely contains the circle. This is clearly an upper bound for the area, and we'll call this upper bound U6. So for instance, I have that the area of the circle is bigger than or equal to L6, or really, I guess, Ln. By Ln, I mean L sub n, not natural log, for any n, and the area is less than or equal to Un for any n. I want to come over here and look at one more little detail. So this is a little bit of an aside. If I have the area of a circle, and let's say I have a circumscribed square, So this is the smallest square, the smallest four-sided regular polygon that contains the circle. So this is U4, and maybe I'll do red for an octagon. If I have a circumscribed octagon, we're not going to prove this carefully, but a circumscribed octagon, there's one note trying to be helpful. A circumscribed octagon has area U8, and I can see that this octagon it contains the same area inside of it that the square contained, but it's missing these four little corners here. So I see, for instance, that U8 is less than U4, but it's bigger than the area of the circle. So what we're just gonna look at an arbitrary n. If we really wanted to tighten up this theorem and make it really tight, we'd either need to prove that something like un plus 1 is less than un for all n, and something similar for ln, that ln plus 1 is bigger than ln for all n. Or we could use a simpler argument using squares and octagons and things, and use something like u2n plus 1 less than u2n, which would probably be easier and would get us the same result. So, and a little detail here that we're not really going to clarify, but just a little aside there. So the higher n is, the better the approximation will be. That intuitively feels right. If we have more sides to our polygon, it's going to fit the circle better. And we can prove carefully that it's right pretty easily in the case of like 4 to 8 to 16 to 32. And you know, the general n case might be harder to prove. Honestly, I'm not sure if it holds for the general n case. It seems like it should, but we could certainly prove it for the 2n case. So we could prove it for the 2n case. We're not going to go through the details. I think it's pretty obvious that how the geometry works out, that if we went from an octagon to a 16gon, we'd be just slicing off some more little pieces of area around there. And then we could, worry about making all of our ends over here 2n's, and or not 2n, 2 to the n. Right, we want 4, 8, 16, 32, u sub 2 to the n plus 1, and u sub 2 to the n. So you see why I don't want to write all of these 2 to the n's and 2 to the n plus 1's, and like in the subscript, it's going to get pretty messy. So this is our little aside. We're cheating a little bit over here, but we could tighten this up and make this a very formal and rigorous proof if we wanted to. It would just be a little more cumbersome notation. Okay, so now my question is, what happens as n goes to infinity? If it's true that ln goes to a number, let's just call it k, and un goes to k, then by the squeeze theorem, the limit of a, well, a is just a, its limit is just the area that it's been all along, has to go to k. So the area of the circle has to equal whatever that common limit is by the squeeze theorem. So this is the overall structure of our proof. We have a regular polygon inscribed, a regular polygon circumscribed. That gives us a lower and an upper bound. I think I kept those in the right order. We can apply the squeeze theorem. And if we can evaluate both of these limits, limit n goes to infinity of ln and un, and if they both go to the same number, then that number has to be the value of a, the area of a circle. I'm going to leave it as an exercise to do the ln bit. And it does end up working out. It does end up that ln goes to the same number that we're going to see as the limit for un. So it does end up working out. It works out as we'd expect, and as we probably guess, it works out that both of these, ln and un, converge to pi r squared. We're going to do the computation for un. So when you rewrite your notes or go back through your notes, go through the ln, see if you can do it by yourself without referring to these notes, following a similar strategy. If you get a little stuck, refer to the notes. The trig will be a little bit different. Whatever which trig function we're using and so on will be a little different, but similar, pretty similar idea. Okay, so for un, what do we have here? Well, we have a circle of radius r. Let's write that down. Circle of radius r. And let me see, can I just move this? Move left. All right. I didn't know that existed until one time when I accidentally right-clicked and then, okay, so now I have my black and blue pens next to one another. Make this a little easier. Okay, so I have UN, an n-sided circumscribed polygon, and one of its sides, say, looks like this. I have two, like, maybe super radii going from the center out to the corners of this polygon. These lines here are going to be longer than a radius r, but coming right down the middle is a line of radius r. I have a 90-degree intersection here. We can actually see using implicit differentiation that the radius line of a circle will always be perpendicular to the tangent line to the circle at that point where it intersects the circle. So we have a 90-degree here. And we have two right triangles now. I also, maybe I'll use red for this. I also have a total of 2 pi radians all the way around the circle. But I have n sides to my polygon. So I have 2 pi over n is my total angle there, right? That total interior angle is 2 pi, the whole number of radians all the way around, divided by n for the n sides, right? This whole thing is one side. Okay. But that tells me that each of these, say this one, for instance, is 2 pi over n, but only 1/2 of that, or that ends up being just pi over n. So I have pi over n radians in my right triangle, if you get what I'm saying, and I have pi over n radians on that angle in my left right triangle. So I now have, if I rewrite this over here to make it a little bigger, I have a side length r. I have a side that's my that's half of my edge of my regular polygon, and I have a side that's like a super radius. Here's my circle kind of coming along like this in here. This is 90 degrees. And this is pi over n. I would like to know the area of, say, this triangle here. What's that area going to be? And then I'll double it to get the area of this whole bigger triangle, this triangular slice over here. And then I'll multiply by n, because this is only one of n sides that I'm accounting for in my regular polygon. So I'll find this area and then multiply it by 2n. I'll double it to get the other half of the other left triangle down here. and then multiply by n to repeat this n times going around for each of my n sides. Well, I have a height. I need to know my base width. And then, of course, my area is 1/2 times the base times the height. So my height is r. What is my base? And here I see that I need to relate an angle, its adjacent side and its opposite side. Tangent is opposite over adjacent, or tan pi over 2 is the opposite, the base, over the adjacent of r. Or the base is going to be r tan pi over 2. And then finally, my area UN is going to be, well, it's the area of this triangle. So 1/2 times the base times the height, but the height is just r, so we pick up a second power of r. And then remember, this is the right side of this bigger triangle, so the left side has the same area. I would double the area. And that accounts for one of the n sides of a regular polygon going around. We have to multiply by n to account for all of the n sides. So un, the 2's cancel, and I have n r squared tan pi over 2. Where did I get pi over 2 from? I can't read my own writing. Not pi over 2, it's pi over n. Pi over n, pi over n, pi over n. So change those pi overs to pi over n. I was getting all excited about my 1/2 canceling the 2 and was got that n mixed up there. So there, change all those to n, and that's my un. So now I see that as n goes to infinity, as I'm looking at a circumscribed area using a regular polygon of more and more and more sides, well, tan of pi over n goes to something like tan of 0 or 0. So this bit is going to 0, but this bit is going to infinity. So I'm ending up with an indeterminate form that looks like infinity times 0. The factor of n at the front makes the whole thing want to get big, and the factor of n in the tan of pi over n makes the whole thing want to go to 0. There's a tug of war between the two. What happens? Does one win out and the whole thing be 0? Or does the other win out and the whole thing be infinity? Well, kind of clearly neither of those is the case. So let's see what this limit ends up being. This is a infinity times 0 type limit, and we've kind of seen this before, that we can make an infinity look like a 1 over 0. Or sorry, look like a 1 over 0. So I want to take my n and put it in the denominator. And putting the n in the denominator gives me a 1 over n. So infinity looks like 1 over 0, which looks like 1 over infinity. But now what I see is that I have a 0 over 0 type limit. The numerator, if I put the limit inside of the tangent, pi over n as it goes to infinity, that goes to 0, tangent of 0 is 0 in the numerator. And the denominator, 1 over infinity, that also goes to 0. So I can L'Hopital this. So I'm taking d by dn of the numerator, d by dn of the denominator, and taking the limit of that ratio. The r squared just kind of comes along for the ride. In the denominator, I have an n to the minus 1. That's negative 1 over n squared when I take d by dn of that. In the numerator, the derivative of tangent is secant squared. Secant squared pi over n times the derivative of the inside times d by dn of pi over n, which is negative pi over n squared. And I see I can multiply top and bottom by negative n squared, and I get this pi sticks around. If I multiply by negative n squared on the top, I just end up with secant squared pi over n left over. And if I multiply by negative n squared on the bottom, I just get 1. And it almost seems like I've backed myself into a corner now because I still have like a trig function evaluated at pi over n, but this actually turns out pretty nice. As n goes to infinity, I get secant squared of pi over n, but that goes to secant squared of 0. But the secant of 0, well, that's just 1 over cos of 0. That's just 1. So this is pi r squared times 1, or just pi r squared, exactly what we wanted to show. So we've shown that limit n goes to infinity of un is pi r squared. Once you complete the exercise and show that ln also goes to pi r squared, then our proof will essentially be complete and rigorous. The only thing that, we might balk at is what I kind of mentioned over here, but we could pretty easily tighten that up by just choosing subscripts that are 2 to the power n to work with, and that wouldn't really qualitatively change anything. It would just be a lot more notation to keep track of. Any questions on that one? So proving even things that are kind of simple in some sense, in the sense that lots of people have known the answer to the question for many years of their life, proving it carefully is not always trivial. Okay, and then last example, let's evaluate this. Limit x goes to 0 from above, sine x to the x power. So here I have something that looks like a 0 to the 0 type limit. The 0 in the base, well, I kind of say like 0 to any power. That wants to give me an output of 0. But the 0 in the exponent, like anything to the 0 power, that wants to give me an output of 1. So if I have some small number to the actual 0 power, I get 1. If I have 0 to the some small number power, I get 0. There's kind of a tug of war here. Who wins? Is the answer going to be 0? Is it going to be 1? Or is it kind of like tied somewhere in the middle? Okay, so we do have a bit of an issue here. This is not a L'Hopitalable form. It's not 0 over 0 or infinity over infinity. And we can't do basic algebra just like we did up here to kind of manufacture a 0 over 0, infinity over infinity. Something like 0 times infinity, a lot of times we can just do basic algebra to fix that. Well, here, what am I looking to do? Well, if I could get a 0 times infinity out of this, that would be nice. And really the difficulty here is that I have a variable in the base and a variable in the power. We've seen an approach to this before where we use the logarithm to kind of bring that power down and do the evaluation. So let's say that y equals limit x goes to 0 from above, sine x to the x. Maybe I won't call it y because that feels like it should be a variable. Maybe I'll call it like k for a constant. Well, if I log both sides, log k, I'm looking for k, so I need to remember this at the end. At the end, if I get some number out, if I get log k equals number, I need to kind of undo that. So I need to remember that. So log k equals the log of the limit of sine x to the x. Since log is nice and continuous for positive x's, for positive inputs, I can move the limit in or out of the log. Usually I move the limit inside of continuous functions, but here I can choose to move the limit outside of the log. That's limit of log. Let me try to write a little cleaner so we can tell which ones are limits and which ones are logs. And log of something to the power is the power can come out in front of multiply. It's going to be power times the log of the base. So it's x log sine x. Now, if I just kind of naively try to plug in 0, I get something that looks like a 0 coming from the factor of x. The sine x looks like a 0, and log of 0 looks like an infinity, looks like minus infinity, but we have something that's overall of the form 0 times infinity. That's kind of what we saw up here. And we also saw really a very similar limit in one of our first examples, limit of x times log x. What was our trick here? We switched this x into a 1 over x. Like that. And now if I just kind of naively think of plugging in 0, I do see that my numerator goes to log of 0, or that's an infinity, minus infinity, but an infinity. And my denominator is x goes to 0 from above, 1 over x. That also goes to infinity. Now I do have an infinity over infinity type limit, and that's the type of limit that L'Hopital applies to. So I had to kind of manufacture this special form to be able to use L'Hopital. But I can use L'Hopital here. Differentiate the numerator. The derivative of log of stuff is 1 over stuff. So 1 over sine x times the derivative of sine x, which is cos x. And then in the denominator, I differentiate 1 over x to negative 1 over x squared. What do I get here? Limit x goes to 0 from above. Well, this cos x behaves pretty nicely. Cos of 0 is just going to be 1. Let me just break it out as a factor. Then I have an x over sine x. And then I have a negative x. Right? That 1 over x squared in the bottom comes up top as an x squared over sine x. And I'll break that apart this way. And I'll stick my negative sign on the x. Now the limit of the product is the product of the limits, so long as the limits all exist. But I know the limit goes x goes to 0 of cos x is cos of 0 or 1. I know that the limit x goes to 0 of the ratio of x to sine x is also 1. Usually we see this as limit of sine x over x equals 1, but of course limit x over sine x is going to be 1 as well. If we really wanted to, we could write x over sine x as 1 over sine x over x, put the limit in the bottom, and then get a 1 there. So either way. And then the limit x goes to 0 from above of negative x is just 0. 1 times 1 times 0 gives me 0. And I do have to remember that log k is 0, where k is the thing that I'm actually looking for at the end of all this. The log of what is 0 of 1. So this limit turns out to be 1. Any questions on any of this? Questions on L'Hopital? Okay, so let's jump down to the graphing section. In case anybody joined a little bit late, I did save the notes as a PDF, which I just put into chat again. So if you didn't get the notes in chat when I posted them earlier, if you joined a little bit later, I just posted them again. There are quite a few definitions and things here. You can see all of this typing. So this way you don't have to worry about furiously trying to scribble down everything that's on the screen. You can focus more on the parts that we'll be filling in. Okay. Okay, so again, we're lumping kind of all these sections of graphing together and just looking at a general strategy for graphing functions using basically all of the interplays that we've seen so far between algebraic structures and graphical structures, and some extras that we'll kind of develop along the way. All right, so first off, what does it mean? What is the definition when we say that, say, a function is increasing on an interval or that it's decreasing on an interval? Note that there's the concept of increasing versus non-decreasing, and then decreasing versus non-increasing. I'll usually not be super careful about the two. Like I'll call non-decreasing or increasing, probably just call them both increasing. But hopefully the context makes it clear. So if it's true that in some interval AB, we pick two numbers, x, y, and if it's true that if x is bigger than y, then f of x is bigger than f of y, so larger input yields larger output, then we say f is increasing on AB. If a larger input yielded an output that's greater than or equal to the other output, so if this was a greater than or equal to instead, then we would say non-decreasing instead of increasing. So just because like increasing relates to non-decreasing and decreasing relates to non-increasing, I think it's sometimes a little more confusing to be super careful and make that distinction. It can be more confusing pedagogically to gain that little tiny bit of precision. So that's why I typically just say increasing or decreasing. So if a larger input yields a larger output, then the function is an increasing function. And if a larger input yields a smaller output, then the function is a decreasing function. Right? So an increasing function looks like this. If the input gets larger, the output gets larger. A decreasing function, if the input gets larger, the output gets smaller. So that's the definition of increasing function. And we have a theorem. If the first derivative is positive on an interval, then f is increasing on that interval. And if the first derivative is negative on an interval, f is decreasing on that interval. And our proof actually looks kind of similar to a couple of proofs we've used before, or we've seen before, using the mean value theorem. So the mean value theorem, this is kind of a sketch of the proof, but it says that f of x minus f of y, as kind of an aside, we're clued into using the mean value theorem because we have information about the derivative, and we want to relate inputs to outputs. How do inputs and outputs relate to one another through the derivative? Well, by linear approximations, but that's approximately equal to. If we want exactly equal to, then we relate them through the mean value theorem. Right. And if, let's say that we do the first case where f prime is bigger than 0, f prime of c is bigger than 0, and if x is bigger than y, and x minus y is bigger than 0, so this is bigger than 0, which means f of x is bigger than f of y. So if the derivative is positive, and if x is bigger than y, then f of x is bigger than f of y. I left out some of the details that we have gone through very carefully in previous proofs. So we should really say, consider an open interval a to b on which f prime of x is bigger than 0. Choose two points x and y so that the closed interval x to y is a subset of a subinterval of the open interval AB. Then we apply the mean value theorem. The mean value theorem applies because f is differentiable on AB, so it's differentiable on open xy and continuous on closed xy, right? All of this preface that we've done, I think, twice in 2 previous proofs, that all really should be here. So this is really kind of a sketch. The kind of crux of the problem, the crux of the proof, is that once we get down to the mean value theorem, we can say that assuming the derivative is positive, if x is bigger than y, then this bit is positive. The product of 2 positive numbers is positive. So if x is bigger than y, then f of x minus f of y is bigger than 0. Therefore, f of x is bigger than f of y. Bigger input yields bigger output. And the other part, if f prime is negative, a negative times a positive is negative f of x less than f of y when x bigger than y. So if the derivative is negative, that switches our inequality sign here, and then a bigger input yields a smaller output. F is decreasing on that interval. Okay. So, I mean, this isn't a super formal or careful proof, but I think it's not a bad exercise for you to go and fill in all of the details. And you have a couple models of that from our last class. Okay, we have a theorem, the first derivative test for max or min. If c is a critical number of f, so either f prime of c equals 0 or f prime of c doesn't exist. And if f prime changes sign from positive to negative at c, so we have c a critical number, and f prime changes from positive to negative, so f prime positive and f prime negative, which means we're increasing and then we're decreasing on the other side, then f has to have a local max at c. When we say, from this to that, we always are in the context of moving from the left to the right. If f prime changes sign from negative to positive, well, that means we had to decrease into the critical. I don't know where that came from, but we had to decrease into the critical point and then increase out of it. That's got to be a local min. And if f prime does not change sign at c, then f has neither local max nor local min. How can that happen? Well, for instance, something like the cube root function does something a little bit like that. I've exaggerated it a little bit, but it does get a horizontal tangent right here at 0. Of course, x cubed, derivative 3x squared, plug in 0, you get 0 for the derivative. But you can see it's actually increasing the whole time. Well, not the whole time, at horizontal tangent for just that instant, but to the left and to the right, in both cases, it's increasing. And this point is, of course, not a local, it's not a local max, because if I go just a smidge to the right, I get a larger output. And it's not a local min, because if I go just a smidge to the left, I get a smaller output. So we can look at the first derivative changing sign at c to tell us whether it's a local max, local min, or neither. And now on to some discussions of the second derivative. So definition. If the graph of f lies above all its tangent lines on AB, so there's some function f that maybe looks like this. And I noticed that sometimes the function f lies below its tangent lines, but at other times, if I draw the tangent lines, f always lies above its tangent lines. So for each tangent line, we have the point of tangency. And if we go to the left or the right, f uh, f of x is always bigger than whatever you want to call it, L of x, let's say. So basically we have like f of x bigger than L of x, bigger than or equal to L of x on some interval. And this L of x is whatever point of tangency we want to choose in that interval. We call this being concave up. It's kind of shaped like a cup. Or in the instances when f lies below its tangent lines on some interval, we call that being concave down. It's shaped like a hill. We have a theorem. If f double prime is bigger than 0 in an interval, if the second derivative is positive on an interval, that tells us f is concave up on that interval. If the second derivative is negative on an interval, f is concave down. So the sign of the first derivative tells us whether the function's increasing or decreasing. Positive first derivative function's increasing, it kind of slopes up basically. And f prime negative, it's decreasing, it slopes down. The second derivative tells us about concavity. If the second derivative is positive, it's concave up, it looks like a cup or like a valley. And if the second derivative is negative, it's concave down, it looks like a mountain or a hilltop. The proof is kind of similar in nature to the proof that I sketched up here. So it's similar to this one, using kind of the mean value theorem on f double prime, relating it to f prime, which of course gives us our tangent lines. And we have a definition that P is what we call an inflection point of f if two things hold. If f is continuous at P and if f changes concavity at P. So I might have a point, say like P here. I guess P would really be this point. So here I go from being concave down to concave up. If I go just a little bit to the left of this input C, or a little to the left of this point P, then I'm concave down, a little to the right, I'm concave up. I change concavity at P. That's what I call an inflection point. Where is that here? Note that this only applies if f is continuous at P. I could have like, some of my like secant and cosecants and all of that have these like crazy asymptote kind of deals. I do change concavity from say concave down to concave up, but I'm discontinuous there. So that's not an inflection point. That's just a vertical asymptote. So I want my function to be continuous at the point and change concavity there for it to be an inflection point. And we have another theorem, the second derivative test for max or min. So here, if f double prime is continuous at C and f prime of C is 0, then we can say that if f double prime is positive, if f double prime at C is positive, then f has a local min at C. This is a little strange. F double prime positive, we have to think about this for a minute. F double prime positive means we're concave up. Well, yeah, that does check out that a positive second derivative indicates a local min. And if the second derivative at C is negative, then f has a local max. If we're concave down, that's going to indicate a local max. So it's a little bit backwards, sometimes until you kind of get used to it. Positive second derivative, I always just say, like, think about the geometry. Positive second derivative means we're concave up like a valley. And in a valley, you have a local minimum. And second derivative negative means we're concave down like a mountaintop. And a mountaintop, you have a local maximum. So think about the geometry of it, how it relates to the concavity, because it is a little strange when you look at it that the positive second derivative relates to a minimum and vice versa. So we have two tests for finding maximum and minima, first and second derivative test. Note the first derivative test, all that we require is C is a critical number of F. F doesn't even need to be differentiable at C. So we could apply the first derivative test. I tried to draw like an absolute value kind of deal here. We could apply the first derivative test even whenever we have a critical number where the derivative doesn't exist. Perfectly fine to apply first derivative test there. We could not apply the second derivative test in a case like that because F prime at C doesn't even exist, let alone F double prime being existing and being continuous at C. So for the second derivative test to apply, for us to be able to apply it, we need quite a bit more. We need two derivatives to exist, and the second derivative has to be continuous at C. Right. So the second derivative test a lot of times is kind of a little nicer to apply. You just take the second derivative, which you're likely to be taking anyway, which we'll see in the strategy down here, and you evaluate it. But the first derivative test, a little more of a pain because we have to look at, a little bit to the left of C, a little bit to the right of C, evaluate F prime in both of those places, see if F prime changes sign. A little bit more of a hassle maybe sometimes, but it applies much more generally. Any questions so far? Okay, so what is our strategy from graphing functions, kind of bringing all of this together? So if I have a function like, say, this quartic function, and I want to draw a graph of it by hand, I could use a table and a bunch of values, but that's a whole lot of work. And it doesn't apply to some examples like this, for example. One of the big actual applications, I want to point this out because, the natural question is, well, why don't we just go to Desmos or plug it into the calculator? Well, we have families of functions like the normal distributions or functions like this one that we might want to draw, but they have parameters, right? There's like M naught, which is a parameter. Or we have like our normal distribution here, X is the variable, mu and sigma are parameters. So these are families of functions. I would like to get an idea of what the shape of a typical function is in this family of functions, but I can't plug this into the calculator. I could maybe choose a bunch of different mu's and a bunch of different sigmas and graph a whole bunch of them and get an idea experimentally what it looks like, but that's at the very least, that's a lot of work anyway, and that could lead us down, that could lead us to some wrong conclusions. So what is our strategy for graphing functions? Well, the first thing is start with the basic algebra. So for instance, finding X and Y intercepts, analyzing symmetry, is it an even or odd function? Does it have translational symmetry? Is it kind of a trig function? Find any obvious points of interest. So maybe there's not an intercept that's a point of interest, but maybe there's another point that we can clearly see, oh, if I plug in this number, like here, for instance, if I plug in X equals mu, other things simplify a lot. That might be a nice number to try to plug in. So if there's any obvious points of interest, let's start there. Second, find our asymptotes and end behavior. Is there any real number A where limit x goes to A f of x equals plus or minus infinity? That's a vertical asymptote. Or what happens whenever I let x go to plus or minus infinity? Does that go to just a real number, giving me a horizontal asymptote? Does, f at infinity equal infinity shooting off to the top right, or negative infinity shooting off to the bottom right? That would be helpful to know, and same with the left. So find our asymptotes in our end behavior. Third, find the intervals of increase and decrease. In other words, the intervals over which f prime is positive and the intervals over which it's negative, where the function is increasing versus decreasing. And building directly off of part 3, we can find the locations then of all the extrema, all the local maxes and mins. And then 5, essentially do the same thing for the second derivative, right? 3 and 4 are the first derivative points of interest. Concavity and inflection points these are the second derivative points of interest. An important note here is don't take this too literally. There might be, well, for this problem, for instance, maybe it's really difficult to find x-intercepts, right? Maybe solving f of x equals 0 is really difficult, or even not possible in terms of, nice functions and so on. E to the x plus sine x equals 0, like, well, good luck solving that. So don't take this too literally. Finding the x-intercept is something that's going to take a very long time to do. Well, maybe skip over that. Come back to it if you need it. If you really need to invest that time to do it, maybe do it. But you might be able to get enough information from everything else that you don't need to. So take the individual problem, strategize based on that problem. But kind of as a general rule, the further we get on this list, the more challenging the material is. And the second note to kind of remember what the order of things here is, well, one is basically just do all the algebra, all the stuff that would be covered in, say, between Math 90 and Math 108, or maybe a Math 111. Step 2 is basically the pre-calculus, the limits and those kind of things. 3 and 4 relate to the first derivative, and 5 is basically the same as 3 and 4, just applied to the second derivative. Okay, so let's take a look at an actual example and try to apply all of this theory that we just built up. So we're looking to graph the function x to the fourth minus 2x squared plus 3. Let's give it a name. Let's call it f of x, so we can refer to it a little more easily. Okay, so let's do the basic algebra first. Well, I can find a y-intercept pretty easily. F of 0 equals 3. Y-intercept is 0, 3. Can I find an x-intercept? I think I have a shot at finding an x-intercept. I can let, I was going to use y, but I kind of, want to use y here. So let me use, say, w equals x squared. So I have w squared minus 2w plus 3 equals 0. So now I'm trying to find an x-intercept. Does this factor? Well, I need two numbers that multiply to make plus 3 and then add to make minus 2. I don't think that's going to work too nicely. I can probably solve for w in, well, I can definitely solve for it in terms of a quadratic formula, and then I can try to square root things. That seems like a hassle. If we really need to, we'll come back and find the x-intercepts. But I did get a y-intercept of 3. Let me maybe circle that in green. I also note maybe that I have x to the fourth and an x squared term. I actually have an even function. F of negative x is the same as f of x. The negative on the x's gets squared off by the fourth or the second power. This is an even function. F of negative x equals f of x. So its look is going to be symmetric about flipping it over the x-axis or the y-axis. Are there any other obvious points of interest? Not really that I see. Maybe we could plug in like x equals 1 or something and get like 1 comma 2, but that seems like kind of a random point. So I could plug in a couple other points if I really want to dial in my graph at the end if I need a little more information, but this is what we got easily from the algebra. Okay, second, let's look at the pre-calc. Do we have any vertical asymptotes? Are there any real number points that limit x goes to a gives me plus or minus infinity? Well, no. This is a nice continuous function being a polynomial. So no vertical asymptotes. If I don't find something that's actually a point of interest, potentially. So knowing that there are no vertical asymptotes tells me, that's a restriction on what my function can look like. So I will actually include that as something somewhat interesting. What about the end behavior then, or horizontal asymptotes? Well, f at infinity is infinity, right? If I plug in a large input, I get a large positive output. The x to the fourth term dominates, and it has a positive coefficient. And then, of course, with it being an even function, I can clearly see that f of negative infinity equals infinity as well. So at this point, I kind of know that I go through 0, 3, and I know I point up in both of these directions, but I really don't know much at all about what happens between the anchor point or anchor points that I have and the end behavior. And this is often the case with just the algebra and pre-calc stuff. I could do something like this. I could do something like this. Something like that. Even if I know generally what quartic functions look like, all of these are still possible kind of intermediate pictures, or whatever intermediate ranges on this picture. So how do I fill this in? Well, one thing that I would like to know is, where's my function increasing and decreasing? Is it, say, decreasing on minus infinity up to 0 and increasing on 0 to infinity with, say, 1 local minimum? Well, then it would probably look something like this. Or does it have a couple different intervals of increase and decrease and some changes in concavity with some different, with a few different local maxes and mins? Well, then it might look something more like this. So that's what I'm going to investigate next. I'm going to find f prime of x. It's 4x cubed minus 4x plus 0. And here what I want to do is I want to figure out when is f prime positive and when is f prime negative for what inputs. So let me draw a number line here. And I want to ask, when is f prime equal to 0? Well, f prime equals 0 whenever 4x times x squared minus 1 equals 0. So just factoring out 4x. Or when 4x times x minus 1 times x plus 1 equals 0. So when x equals 0, 1, or negative 1, these are the zeros of f prime. F prime is just a function, right? F prime is a continuous function, 4x cubed minus 4x. These are the only zeros of f prime. If I want to find intervals of increase or decrease, if I say test a point -2, and I find out that for instance, let's say f prime is positive there, well then this function 4x cubed minus 4x would have to be positive on that whole interval to the left of -1. If it say switch to negative at -1.5, well, I have a continuous function over an interval where I am positive at one point, negative at the other point. There has to be, by the intermediate value theorem, another zero there, but there's no other zero there. There's no zero between -2 and -1.5, right? So I can actually see that I can pick one point in this interval, one point in that interval, one in that one, and one in that one. I can pick 4 test points, and whatever sign my test point ends up being, because I found all of the zeros of f prime, whatever sign my test point ends up being, f prime on that entire interval has to share that same sign. So let me start over here. Let me try maybe 2. What is f prime of 2? Well, f prime of x I see is 4x, x minus 1, x plus 1. F prime of x is that. F prime of 2 is, I only care about the sign, right? So 4x, when I plug in a positive number, is positive. X minus 1, when I plug in 2, 2 minus 1 is 1, it's positive. And 2 plus 1 is positive. So f prime of 2 is positive. We're increasing on the interval 1 to infinity. I'll pick a test point between 0 and 1, maybe like 1/2. F prime of 1/2, well, I plug a positive into 4x and I get a positive. If I do 1/2 minus 1, that's negative. 1/2 plus 1 is positive. Positive times positive is negative. So f prime is actually negative on 0 to 1. I could pick 2 other test points in the other intervals, or I could note f itself is an even function. F prime is an odd function. That means if I flip across the y-axis, my signs of my outputs flip. This has to be positive. This has to be negative. So I see f is increasing on what? Where is it positive? Where is f prime positive? -1 to 0, union 1 to infinity. And f is decreasing on -infinity to -1, union 0 to 1. I also see that I change sign from negative to positive. Changing sign from negative to positive is a local min. So I have local minima at x equals -1 and at x equals +1. And I change sign from positive to negative, so going up and then down, indicating a local maximum at x equals 0. So this is kind of part 4 that I get almost basically for free off of that picture. So now I have a lot more information to fill in the middle here, right? I have a local max here at -1 and at +1. I have local minima. Maybe I'll figure out what is f of 1. Well, f of 1 is 1 plus 3 is 4, minus 2 is 2. So f of 1 is 2. Right? So 1 comma 2, I have a local min. And then by the evenness of the function, I have a symmetric bit over here. So it looks like it's going to kind of come down, go up, come down, go up. I will draw it a little bit nicer in a minute here, but I do see that at this point, I probably have enough information to graph this in a way that, makes me pretty confident that I know what's going on. So at this point, I'm probably pretty happy with my ability to graph this. Let's go through number 5, though. Check the concavity just as an exercise. I think it's a little bit overkill for this problem, but it actually won't be hard at all to do for this particular problem. F double prime of x, f prime of x was just this cubic, 4x cubed minus 4x. If we differentiate that, we get 12x squared minus 4. And again, I want to do this same idea of taking a real line, splitting it into intervals of concave up and concave down, or where the second derivative is positive or negative. I do the same strategy. One is f double prime equals 0. Well, that's when 12x squared equals 4, or when x equals plus or minus 1 over root 3. Remember, f is even, so f double prime is even. F is even, f prime is odd, f double prime is even. I'll pick a couple of test points, maybe 0. So f double prime of 0 is -4. F double prime is negative in this middle interval here. It's concave down. The function is concave down in this middle interval. And I can pick a number like maybe, say, 1 that's above 1 over root 3. Well, that's 12 minus 4 is 8, is a positive number. And by the evenness, I know the sign over here has to be the same. So I see I'm concave up on the interval minus infinity to minus 1 over root 3 union 1 over root 3 to infinity, and I'm concave down on minus 1 over root 3 to plus 1 over root 3. And I see, of course, f double prime is continuous. It's a quadratic. And I see that I have inflection points at -1 over root 3. I change concavity there, and 1 over root 3. Does this kind of mesh with my sketch up here? Yeah, sure. I was concave up, concave down, concave up. Looks good. So if I want to rewrite this a little bit nicer, I see that my function goes through 0, 3. It has local max there, but it has local minima at plus or minus 1, comma 2. So these are important numbers. So I have a local min here and there, and a local max here. It's an even function, so this should look pretty symmetric from one side to the other, or differential everywhere. So that shouldn't look like a kink there at -1, but that's just the flaw of my artistic ability. And we're shooting up to positive infinity on both sides. Okay. And we're kind of happy we didn't try to find x-intercepts now. It looked like it was going to be a bit of a mess if they did exist. And in fact, they don't exist, our x-intercepts. So, we could have applied quadratic formula, but then our w's would have been negative, and then x squared equals negative number. That's not going to work so well. If you want to, just as an algebra exercise, use the quadratic formula to show no x solutions exist, or no x-intercepts exist, no x solutions to this equation exist. You will get w solutions, but your w's will be negative numbers, and then finding an x so that x squared equals negative number, that's where you get no solutions. So if you want to do a little algebra exercise, you can do that too, to practice some of the quadratic formula stuff and all of that. Any questions on this one? So again, we could have gotten away without doing part 5 here. I think we had enough information to feel comfortable. I did it as just a demonstration. But I think it is important that, as a general rule, you want to strategize based on the individual problem, especially if you're doing, a bunch of homework problems, or especially if you're on an exam. Okay, so warm-up problem to our more complicated problem here. Let's try to graph e to the negative x squared. So let's give this function a name. We can zoom in a little bit, see that a little better. And let's call it g of x. Variety is the spice of life, right? We use g instead of f. So, uh, so g of x equals e to the negative x squared. First, let's do any basic algebra we can. Let's find intercepts. The y-intercept's usually pretty easy to find. E to the 0 is 1. And maybe I'll continue my writing points of interest in green or blue. So our y-intercept, 0, 1. I actually noticed that there's no x-intercept, right? G of x equals 0. E to the negative x squared equals 0. Well, e to the negative x squared is always positive. So there's no x-intercept. But I will note this interesting thing that g of x is strictly positive. Nothing in quadrants 3 and 4, only in quadrants potentially 1 and 2. I also noticed that the only place I see an x, it's an x squared, so g is an even function. So g of negative x equals g of x. This graph should have mirror symmetry across the y-axis. So I actually got a decent bit out of just the algebra stuff, right? It's easy to forget this stuff because we want to jump right to finding derivatives and local maxes and mins, because that's kind of the new exciting stuff. But it's easy to forget some of this basic stuff, and this gives a lot of information about the graph. Now, we're still missing a lot of information, particularly about what happens what happens in between our points of interest that we've located, maybe. So we still need the rest of, or at least a few more pieces of information, but we have some good information, though, just from point 1. So we got algebra out of the way. Now we're on to kind of the pre-calc stuff, the basically limits kind of stuff. Do we have any vertical asymptotes? No vertical asymptotes. And do we have any horizontal asymptotes? Well, g at actually plus or minus infinity. Well, g of x, if I wanted to, I could think of this as 1 over e to the x squared. if I plug in a really big value for x, e to the x squared is a really, really big value, and that's in the bottom, g goes to 0. So I have a horizontal asymptote, y equals 0 at plus or minus infinity. Of course, I expect if I have a horizontal asymptote at plus infinity, it's going to be the same one for minus infinity. I have an even function, so that checks out. No vertical asymptote, though. Right. So I already have quite a bit of information. I have just a little sketch here. Nothing in quadrants 3 and 4, because g is always positive. It's even, so it's got to be symmetric about y. It goes through 0, 1. It's got to have horizontal asymptotes at 0, so it's got to approach from above, right? Because it's got to stay positive. I actually have quite a bit of information about this function, but I don't know what happens in between. Does it kind of wiggle around a little bit? Does it kind of, is it like non-differentiable? Does it have like a cusp here? Um, does it just come up and have a nice local max? Does it change concavity, or does it have another couple of local extrema? There could be a lot of different things that can happen in here. So a lot of times this is what we see is our kind of algebra and pre-calc gets us some kind of anchor points and some end behavior, but these little details, these little nuances that we probably would find interesting and want to clear up, we don't quite get that. We need to go to calculus for that. Okay, so on to our first derivative. We'll kind of just say 3 and 4 at the same time, intervals of increase and decrease, and local max and min. So this is f of x, or g of x, sorry. I went and changed it to g, and I'll probably end up calling it f if I don't have it on the screen. But this is g of x, e to the negative x squared. G prime of x is, well, e to the stuff times the derivative of the stuff is negative 2x. So g prime of x is negative 2x e to the negative x squared. And I want to know, when is g prime of x 0? Well, e to the negative x squared is always positive, so the only place that g can be 0 is at x equals 0. We have one critical point, one critical number. So g prime is 0 at 0. I also know that g prime is an odd function. So the sign of g prime for some test point on the right is going to be the opposite sign for that test point on the left. If I pick a test point on the right, say like the number 1, g prime of 1, well, that's negative 2 times 1 is a negative number times e to the whatever, but that's positive. So g prime is negative to the right of 0. And by the oddness of g prime, it's got to be positive to the left of 0. So we can say that g is increasing on negative infinity up to 0 and decreasing 0 to infinity. And we can also see that we have a local max at x equals 0. We increase into it and decrease out of it. Any questions so far? So at this point, we probably have enough. We know that we're increasing up to a local max, decreasing out of it. That's got to look something like this. It kind of looks like there's an inflection point, right? It kind of looks like we're concave up, then concave down, then concave up. So we might actually be interested in knowing where those inflection points are. That might be a point of interest for us. Let's actually do step 5 as well for this one. So that was g prime of x. Let's compute g double prime of x. We'll be careful with this. Oh, one note. Let me write this over here. I want to remember to just mention this, Darbo's theorem. So I want to remember to mention that. But so g prime of x was negative 2x e to the negative x squared. G double prime, I have a product now of two functions of x. Derivative of the first is negative 2 times the other one, plus the first times the derivative of the second, e to the negative x squared times negative 2x. The negatives cancel, I get a 4x squared. Let me simplify this a little bit. So I can pull out a factor of 2 times some stuff, e to the negative x squared. And I'm left with a 2x squared minus 1. If I did all of that right, that looks good. So that's g double prime. And I'm interested in when is this 0? Looking for inflection points, potential changes in concavity. Well, I have the product of three things that I want to find when it's 0. 2 is not 0. E to the negative x squared is always positive, so it can't be 0. So when is 2x squared equal 1? Or x equals plus or minus 1 over root 2. These are my two potential inflection points, my two potential points of change in concavity. G double prime, of course, is nice and continuous, right? Nothing strange going on with this function. Here's G double prime. It is an even function because G is even, so G prime is odd, so G double prime is even. A good test point to use in the middle might be, say, 0. Well, G double prime of 0 is, well, the number 2 is positive, times 0 minus 1 is negative, times the exponential is positive. That gives me a negative second derivative. In the middle here, it's concave down. That meshes with what we expected from our picture up here, right? Concave down in the middle. Square root of 2 is bigger than 1, so 1 over square root of 2 is less than 1. So I could pick a test point like 1. That would be an easy one to plug in. Trying to write my test points small so that we don't think that they're 0 points for whatever derivative we're working with. G double prime of 1, well, of course, the factor of 2 is positive. 2 times 1 minus 1 is positive, and the exponential is positive. G double prime is positive at 1, and since we don't have any other zeros for G double prime to the right of 1 over root 2, G double prime is going to be positive on this whole interval to the right. And by its evenness, also got to be positive to this interval in this interval on the left. And so I can say that G is concave up on negative infinity to negative 1 over root 2, union 1 over root 2 to infinity. And it's concave down on negative 1 over root 2 to positive 1 over root 2. And I think now we can pretty confidently draw our picture. Oh, why did I make my y-axis so tall? So I know I go through the point 0, comma 1. I know that I have horizontal asymptotes that at y equals 0 that I need to approach from the top. My function stays positive where it's got to be mirror symmetric across the y-axis. I see that I am increasing into that local max and then decreasing out of it. It's going to be a global max, in fact. And I see I'm concave up from minus infinity to minus 1 over root 2. And then I change concavity. And then I change concavity again on the other side. So these plus and minus 1 over root 2, that's like, well, root 2 is about 1.4. 1 over root 2 is, say, something like 2/3. So if this was like 1 here and negative 1 here, maybe I change concavity somewhere in this ballpark. So I'm concave down. Then I change to being concave up. I'm concave down, change to being concave up. So something like that. I should have this mirror symmetry. I go from 0, 1. That's my local max and my absolute max. And then I want to kind of decrease as I fall away on either side. I don't have any kind of local maxes or mins on either side, nothing like that. I certainly don't, have a local min here or anything like that either. So I think I'm pretty happy with this graph. Kind of a simple graph, but we had to do a lot of checking to make sure that it wasn't more complicated. One little note that I want to mention is, so this strategy here, where I say, okay, I take, well, here, we'll talk about this one, where I say I take the derivative, I figure out when is g prime equal 0. I set those anchor points. That splits my real line into some different segments, and I just take a test point in each segment. I leaned heavily on the intermediate value theorem property applying to g prime. If g prime exists, that implies that g is continuous. So the intermediate value property definitely applies to g without question. The intermediate value theorem applies there. But we're kind of using a little too much, right? We have a g prime. G prime exists, but g prime might not be continuous. Now we could just check g prime. I could look at this and say, okay, yeah, g prime is continuous. Or I could have done that in the past, the last example as well. I pointed out that g prime was a polynomial, therefore it's continuous, and we can apply the intermediate value theorem. Is this something that I need to do every time? The answer is actually no. There's a theorem called Darboux theorem, and it says that if we're dealing with a function that's a derivative of another function, if we're dealing with a g prime that's the derivative of some other function, g of x, then the intermediate value theorem property applies even if g prime is not continuous. So we can do this kind of a process, find all the zeros, split them up into intervals, and pick a test point, and we can't jump across the zero even if all of the assumptions of intermediate value theorem are not satisfied. So Darboux theorem basically says, okay, I mean, we were reaching a little bit here to try to make the argument that we can do this strategy for any function. Part of our strategy wasn't, check to see if g prime is continuous, and if it is, then do this. We just said do this. And the thing that saves the day is Darboux theorem. So just a little side note there. The intermediate value property applies to functions that are derivatives of other functions, and g prime clearly, as well as g double prime, if they are both derivatives of other functions, clearly. So Darboux comes in and saves the day and says that this is a valid thing to do. Okay. Any questions on anything from today? So next time our focus is going to be basically to continue on with graphing and look at graphing a few more examples. We might wrap up these last, 4 or maybe 5. Might throw another one on the end here next time, or we might continue into the time after that. These examples obviously take a decent bit of time to do, not just in the calculation, but also in me explaining everything. But even when you're doing them on homework, an example like say this one is probably a 15 or 20-minute homework example. An example like this first one is probably a 10-minute homework example, even when you're used to doing it, right? There's just a lot of individual calculations to do, a lot of algebra, and taking your time and making sure you don't make silly mistakes. So, all right, any questions on anything? I will stop the recording then, and